So the next thing to discuss is when are things going to mix and when are things not going to mix? And you might say to yourself, well, that's all we've been talking about the whole time. We've been talking about when things mix and when they don't mix. But take a look behind me. What I have here is a plot of the Flory-Huggins parameter as a function of composition, at least just schematically. And this is what it's going to look like almost always. I can't think of any exceptions right now, but there may well could be exceptions. But in general, for something like this, remember that if you are below a certain chi parameter, we saw this by plotting the Flory-Huggins equation, you are always going to get mixing down here, right? Because of the reasons that we discussed in the previous video about stability and instability. Now, this curve, or these curves, this outer one is the binodal curve. And the inner one is the spinodal curve. And remember that based on our analysis of the stability of the free energy, or the stability of the system with a free energy that's given by the Flory-Huggins equation, that systems that fall inside of the spinodal curve are always unstable with respect to any fluctuation in composition. So with respect to any d phi. It doesn't matter how small it is. Any small fluctuation is going to lower the free energy of the system, and so that will favor demixing. We also saw that between the spinodal and the binodal curves, the system is metastable. And what I said last time is that this is going to lead to two distinct mechanisms by which the system will demix. Inside the spinodal curve, we will get what's called spinodal decomposition. And then outside, between the binodal and the spinodal curve, so between, not the dinodal, the binodal and spinodal, we will get demixing of our system by a different mechanism, and that mechanism is nucleation and growth. So out here we get nucleation. Let's make that a little cleaner. We get nucleation and growth of regions. And you might expect that you would have two different mechanisms, right? Because inside the spinodal, any composition fluctuation is favored and will lead to demixing. But inside this region, only fluctuations of a certain size I'm not spelling well today. Only fluctuations of a certain size are favored inside here. And by favored, I mean that those fluctuations will lower the free energy of the system. So that's why you might expect just a priori why you would have two different mechanisms, right? Because in one case, all fluctuations are favored. In another case, only large fluctuations are favored. So if I was to guess and take a guess at what might happen, that would be my guess anyway. A couple of other things. Again, look at the axes that I've plotted here. I'm plotting the chi parameter as a function of composition. And when I plot these curves, thinking back to the previous video, I'm plotting chi b as a function of phi. And for the spinodal curve, I'm plotting chi s as a function of phi. And we derived what those equations would look like. So when I started this video, I asked the question, well, when is a system going to mix and when will it demix? And in terms of compositions, we kind of know what that is just from looking at this graph. If it's within the binodal region, in some sense, it's going to be unstable. It just depends, right? The details of how unstable it is depend on what the volume fractions are, whether it's metastable or unstable. But what about chi itself? So how do I know if a certain value of chi will lead to phase separation? Let me give you an example. I said before that if you have polystyrene and deuterated polystyrene, that these two things don't like each other. That extra neutron in the deuterium atom is enough to change the interaction such that in some cases, polystyrene will phase separate or demix from its deuterated counterpart. And in this case, the chi parameter as a function of temperature can be written as minus 0.00017 plus 0.117 divided by T. And of course, T is in Kelvin. So how do I know the temperatures above or below which the system will phase separate? In fact, let me come back to that in a second. Let me give you another example of a polymer. What about polystyrene and polyphenylene oxide, or actually it's poly 2,6-dimethyl 1,4-phenylene oxide. That's a mouthful, so we just call this PPO. So what about this? Well, for polystyrene and this other polymer, this PPO polymer, the chi parameter as a function of T can be written as 0.059 minus 32.5 divided by temperature. So you see the different chemistry in that case gives rise to different interaction parameters. And you see that the A and the B terms have changed a little bit. In fact, we could go back and we could look at this chart that we made, and we could see whether or not we expect the system to exhibit LCST, UCST, or very favorable mixing always. So if we look at the polystyrene and the deuterated polystyrene, we have A is negative and B is positive. If A is negative and B is positive, this is a UCST system. Which means that mixing is favored as T increases. And we could do the same for the polystyrene PPO system. We see that A is positive and B is negative. If A is positive and B is negative, this is an LCST system. So mixing is favored as T decreases, at least in general, right? It turns out that polystyrene and PPO pretty much always mix. This is a really great polymer combination for making essentially polymer alloys. Not many of them exist, but when they do exist, they're kind of important to us. This combination is actually a commercial product called Noril. So it's great when we can identify these. But I just told you that for all intents and purposes, this system always mixes, despite the fact that technically it's an LCST system. It demixes as you heat the system up. So how do I know that? How do I know when something's going to mix and when it's not going to mix? In addition to just looking at the general shape of the curve, if I know something about the interactions, if I know the chi parameter, how do I know? Well, to answer that question, we go back and look at the phase diagram. And you can see that if I pick any particular temperature, any particular volume fraction, and I move up like this, as soon as I cross that binodal point, I'm going to get into the region of the phase diagram where I'm likely to see polymers demixing. So you see that occurs, in this case, for that value of chi. So you could trace this over. This is going to mess up the drawing a little bit, but you could trace this over to the y-axis, and that will be the chi where the system starts to phase separate. I could go over and do this again at another composition, and you could see that the chi where this system is going to start to demix is higher than it was at the other composition. So the question is, what is the lowest value of chi that I can have in my system and still get mixing? And you can see from the shape of the graph that that would be equal to that point there. Okay, so there's a critical value of chi. There's also going to be, I'm going to erase some things and clean up this drawing a little bit. Oops, let's not erase too much. So I'm going to erase this so that I can show you some things. And that is that I'm going to have a critical value of chi. Let's call this chi C. And that's where that yellow point is. And in addition to that, I'm going to have a certain critical volume fraction. So at a volume fraction of phi c, I'm going to be able to, I'm going to get the best mixing. Sorry, I'm not going to get the best mixing. That's going to be the point where I'm going to see phase separation first. If I was to do the same thing that I just did and go up from chi c as a function of chi, then I'm going to eventually see phase separation faster, or sooner, I should say, than I would at those other compositions that I pointed out. So this is a very interesting point for us to try to understand and hopefully calculate, because systems that have chi above chi c, roughly speaking, are the ones that will start to demix, neglecting the fact that that chi parameter is going to interact differently at different volume fractions. Okay, so ignore that for now. But I hope that you can see that finding phi c and chi c is going to be very important. And you can see that if I look at the binodal or the spinodal curves here, first of all, those curves coincide at phi c. So chi b and chi c coincide at that point. And you can also see that that's a minimum. So that means that the derivative of, let's say, oh my God, my notation, not chi c, chi binodal and chi spinodal coincide at that point. And that means that the derivative of chi s with respect to phi a should be 0 at that point. Why? Because that's a minimum. So it's an extreme value of the function. So hopefully I can find those values just based on the fact that it is an extreme value of the function. So that's what we're going to do. We're going to take the derivative of chi s and figure out what is phi c and what is chi c. So that's the first task. One thing that I want to comment on before I go any further is we mentioned UCST and LCST behavior. So that's how my system is behaving with respect to temperature. In the case of this chi parameter, the curve is always going to be pointed upwards like that because positive chi's raise my free energy. So positive chi's in general lead to demixing. Now the specific values are what we're going to calculate. In terms of UCST and LCST temperatures, if I was instead to plot as a function of temperature those binodal curves, then I would get something that looks like this. And instead of plotting chi binodal and chi spinodal, this is going to be T binodal and T spinodal in a UCST system. And the opposite would be true for an LCST system. So I would see something that looks like this. Except those should coincide at the critical point. But the same thing's true. This is going to be the binodal curve and the spinodal curve. But with respect to temperature, depending on the sign of A and B, they'll either be pointed up or be pointed down. I'll just say LCST. But in terms of the chi parameter, if I was to plot the behavior of the chi parameter, it's always going to look like this back here. Okay? All right. So the first task is to figure out what is the critical volume fraction and then the critical chi parameter for my system, because that's going to tell me something about whether or not I'm going to mix or not mix. So we can go back. And last time we derived that the chi parameter on the spinodal, and it's a function of phi a, was equal to 1/2 and then multiplied by 1 over NA phi a plus 1 over NB 1 minus phi a. So again, we're looking for something. If I was to just plot the spinodal curve, we're looking for the extreme value of this function. We're looking for the minimum value of chi above which the system will phase separate. And that point will be given here at a volume fraction of chi c and a chi parameter of chi c. So we just have to take the derivative. So we'll take the derivative, we'll get the critical volume fraction, and then we'll plug that back into chi to see what the value of chi would be. So the derivative of chi s with respect to volume fraction is going to be 1/2 times minus 1 over NA phi a squared plus 1 over NB 1 minus phi a squared. And that will be equal to 0. It doesn't matter. I kind of put the minus sign on the first term. If that's bothering you mathematically, then fine. You could just as easily put it there, okay? Because we've got 0 on the other side, so we can multiply through by whatever. It doesn't matter because when phi a is equal to phi c, then this derivative will equal 0. So actually what I should do above is this is only true if I have phi c. It doesn't matter. If you wrote it the other way, it's fine. You'll just have to substitute in phi c. So we have to solve. Well, this is equal to 0, so I also have that kind of continuing on. 1 over NA phi c squared is equal to 1 over NB 1 minus phi c squared. And that's why I wasn't so concerned about those minus signs. How do I solve this? Well, it kind of looks like a pain, but I have 1 over something is equal to 1 over something. So why don't I just flip the whole thing upside down? So this means that NA phi c squared must equal NB 1 minus phi c squared. And how could I solve this? Well, I could expand everything and collect my quadratic terms and get everything together and use the quadratic formula and try to simplify it. And that's fine if you want to do a lot of work. But why don't I take the square root of both sides? Because phi c has to be greater than 0, so I'm not going to worry about any imaginary solutions or anything like that. So if I'm only interested in the real solutions, then, well, I shouldn't just say that. Not really just the real solutions, but a quadratic equation will have 2 solutions. So I'm only interested in the positive real solutions. So both of them have to be real. If I take the square root the way that I'm doing this, I'm only going to consider the positive value because the volume fraction has to be positive. That's what I mean. Okay, so if I do that, square root of NA times phi c is equal to square root of NB times 1 minus phi c. To go back to that point, what I'm trying to say is you have to be careful when you divide through by the variable you're solving for when you're trying to solve for it, because it could be 0, in which case you're going to miss solutions. Also, you have to be careful in case things are imaginary and things like that. But given that we know the volume fraction is between 0 and 1, it's safe to do what I'm doing. So I just want to put that out there so that if you're doing this in other situations, you don't just do what I'm doing. Okay, off my soapbox. So anyway, now we can expand and collect terms. So we get square root of NA phi A, phi C, and then we'll get plus square root of NB phi C is equal to the square root of NB. And you can see what the solution is. Phi C will be the square root of NB divided by the square root of NA plus the square root of NB. So this is an important result. Now let's just see if this makes sense, right? We have an equation, but an equation is just an equation. It should make physical sense. So if I go back up here, it kind of looks the way that I drew it, that phi C would be about 50%. And remember that when I drew the free energy, when I plotted the free energy in Wolfram alpha, if NA and NB were the same, then things were symmetric. If NA and NB are not the same, then things became skewed. So if NA was bigger, you might get a curve that looks like that. So the point I'm trying to make is that based on this graph, we expect that phi C is going to be 50% if NA is equal to NB. So if I go down here, if NA is equal to NB, and we'll just call this N, then what is phi C? Phi C would be the square root of N divided by 2 square root of N, which is equal to 1/2. Okay? So it makes sense. The math is what it is. And if we think about whether this makes physical sense, then the answer is yes, this makes physical sense. Okay, so we know phi C, then what is chi at that critical volume fraction? Well, chi S is equal to 1/2. Actually, chi S is equal to that, but let's call it chi C because we're going to substitute in for phi C. So chi C will be equal to chi S for phi equals phi C. And that will be 1/2, 1 over the degree of polymerization times phi C, plus 1 over NB times 1 minus phi C. And we'll just substitute in for phi C and see what we get. So chi C would be 1/2. We'll do the first term. So we're going to have NA, and then phi C is what? Phi C is square root of NB divided by square root of NA plus the square root of NB. So we'll get square root of NB square root NA plus square root NB. And then the next term, we're going to get 1 over NB, 1 minus phi C. So 1 minus square root NB square root NA plus square root NB. So what you're going to find is that this term is going to look similar to the first term but it's going to have the Na and Nb in different places. So we're going to have, for this term, square root of Na plus square root of Nb divided by Nb square root of Na. You don't have to take my word for it. You can plug in and check that I did this right. Beauty of mathematics. Okay, so now we've got our terms. So we've got 1/2. The first term, I'm going to break up that fraction into two fractions because I have that sum in the numerator. So I'm going to have 1 over square root Na square root Nb, plus for the second term, the square root of Nb is going to cancel out. That thing will cancel. So I'm going to have plus 1 over Na. Move to the second term. It's going to look the same, but opposite. So I'll have plus 1 over Nb plus 1 over square root Na square root Nb. So you can see that looks a lot like the expansion of a binomial. So a plus b squared, it looks like that. So I've got the 2 times ab. So this is the same thing as 1/2 times 1 over the square root of Na plus 1 over the square root of Nb, and that whole thing squared. So this is also a very, very important result. So now what we've solved for, I'll just redraw it down here. So this is phi A, this is chi, and I'll just, whatever, I'll draw the binodal curve and the spinodal curve. What we've solved for is phi C. And remember, phi C is the square root of Nb over the square root of Na plus square root of Nb. And we've solved for chi C. And that's the minimum value of chi that I can have before the system starts separating. So this chi C 1/2, 1 over the square root of Na, 1 over the square root of Nb squared. Okay, so that's what I solved for. That's all I want to solve for. So what? Well, remember, there's 3 types of solutions that we've talked about: regular solutions, polymer solutions, and polymer blends. So let's take a look at those 3 cases. So for a regular solution, the kind of thing you would study in physical chemistry and maybe a chemistry department in the first semester, we're talking about small molecules. So Na is equal to Nb is equal to 1. So we can just plug in and see what these values would be. It's probably not surprising to you that chi C will be 1/2. Sorry, phi C will be 1/2. And what is chi C going to be? It'll be 1/2 times 1 plus 1 squared. So that's 2 squared. That's 4 divided by 2. 2. So for a regular solution, if your chi parameter is greater than 2, and chi is greater than 2, your system will demix. Now, if you have other volume fractions, chi could be a little bit higher, but ignoring that, the minimum value of chi that you can have and guarantee that your system is stable and will mix is 2 for a regular solution. So when I was plotting the function in Wolfram Alpha, that's how I kind of knew what values to pick to show you the behaviors that I wanted to show you. Okay. Polymer solution. What's that? Well, Na we'll just call N. And the other component's the solvent. That's a small molecule species. So Nb would equal 1. And so the critical volume fraction would be 1 divided by the square root of N plus 1, or approximately 1 over the square root of N. That's another way of saying that your phase diagram is going to shift a little bit. So in this case, when I draw the phase diagram, it's no longer the halfway point. What's going to happen is your phase diagram will shift. It'll be skewed to higher volume fractions. So we kind of saw that. Or sorry, I did that backwards, didn't I? It should be skewed to lower volume fractions. So this term would tell you that your phase diagram would look something like that. It's kind of shifted to lower volume fractions. And what is the chi parameter, the minimum chi parameter you can have and guarantee that your system will mix? Well, that is given by chi c, which is 1/2 times 1 over N plus 1 squared. And if you have a very, very, very big polymer, so if N is much, much bigger than 1, which is usually the case for these big polymers that we're interested in, then chi c is approximately 1/2 times 1 over something very, very, very big plus 1 squared. So chi c is about 1/2 for polymer solutions. Okay. And then the final case is a polymer blend. Well, in this case, Na is going to be really big because the molecular weight's going to be really big. Nb will be really, really big because the molecular weight's really, really, really big. And so what you're going to get, we'll just look at chi c. It'll be 1/2. 1 over something really, really big plus 1 over something really, really big squared. Well, that term in the brackets is 0. And so for a polymer blend, this is about 0. These are the limiting cases, right? Really, really big polymers. If you know the degree of polymerization of your polymer, then you can plug it into the expression and calculate what it should be. So you see, it's not the case that if chi is greater than 0, that things will demix. It depends. If chi is greater than 0 for a polymer blend, yeah, probably it'll demix, almost certainly if the polymers are really, really big. If you have a polymer solution and chi is bigger than 1/2, well, there's a good chance that it's going to start phase separating. And if you have a regular solution, which is here, if you have a regular solution, then if chi is bigger than 2, then it's probably going to demix. And if it's less than 2, then it will mix. Polymer solution, if it's less than 1/2, it'll mix. Polymer blend, if it's less than 0, it'll mix. Okay? So if chi is less than chi c, it will always mix. And if chi is greater than chi c, you need to consider the effect of phi a and see what that does. So it's not as simple. Okay, so that is, or those are the critical points for our solution. And now the last thing to talk about is how things phase separate. So now at this point, we can talk about the two mechanisms by which things will phase separate. And those are spinodal decomposition and nucleation and growth. So what I'd like to do before we talk about this in any more detail is to show you what I'm going to be talking about. And what I've got behind me is a computer simulation from some software that I wrote a long time ago. Man, I was an undergraduate. This is 2004. This is a DPD code. It's kind of like a coarse-grained molecular dynamics code. And it runs on high-performance computing clusters, so supercomputers. And what you're seeing is a thin polymer film. So this would be something like, I don't know, 10 or 20 nanometers thick. And it's got two different polymer components in it. And I'm only showing one component, and that's in red. And what you're seeing is the system go from an initially mixed state to a demixed state, where you can see that the two components have separated from each other and that the size of the separated regions are growing with time. So that's the basic phenomenon that I want to start to describe. This one is spinodal decomposition. The other one I'm going to talk about that I'm not going to show you a video for is nucleation and growth. And then once we complete the discussion, I'm going to show you a couple of more videos that I generated this week using the high-performance computing cluster at Case Western Reserve University. Using the same code, magically the code still works all these years later. I still use this code in my own research. But these original modules that I wrote as an undergraduate for the research that I was doing, they still work just great. So I'm going to show you those in a little bit, but to help you picture what's going on, when I describe what these systems are doing, I really want you to focus in, or at least remember from the video that I'm showing you, what's actually happening. So now that you kind of see what this phenomenon looks like, let me draw a little bit of a schematic. So this is going to be my system initially. So I prepare it the way that I want. So I'm going to prepare it at some initial volume fraction of A, just like we did when we were analyzing the free energy curves. And so initially it's mixed. And then depending on the volume fraction, in other words, depending on where we are, whether we're inside of the spinodal curve or whether we're between the binodal and the spinodal curves, we're going to demix either by spinodal decomposition or demix by nucleation and growth. And so there's a couple of considerations that go into this. When I demix, you kind of already saw what the shape of this is. So let me draw a couple of these domains. So here's one of the red ones. There's another red one. Something like that. And then I didn't show it, but hopefully I can show it later. Everywhere else will be the other polymer component. So this kind of looks like oil and vinegar, if you've ever seen like an oil slick on a puddle in a parking lot or something like that. Kind of looks like that. So there's a couple of things that happen. One is that there's going to be a change in free energy. There's going to be a delta F. And let's say it's per volume, or it's normalized by volume. And that will be the delta F mixing at phi. Oh, this is getting crowded. Let me write it over here. So there will be a change in the free energy per volume. So this will be delta F volume. So an intensive quantity. It doesn't depend on how big my system is. And it's basically going to be the change between the free energy of mixing in whatever final state I end up. So whatever the volume fraction is in that phase, Of course, it's also going to be a function of the degrees of polymerization and chi. So that's the final state minus the free energy of mixing in the initial state. Okay, just roughly speaking. And that is going to go down, right? Because we know that the free energy in those phase-separated regions is lower than it was in the mixed state. And after all, that's largely why the thing is phase-separating to begin with. Okay, so I'm going to have a term from phase separation in the bulk. But what else do I know? Well, because of these interactions, the red component and the blue component that I'm showing back here, they don't like each other. They don't want to be in contact with each other. In fact, they want the minimum number of contacts between each other that are possible. So there's going to be a term that depends on how much surface area these domains have. So there's going to be an interfacial term. And that will be more important when we talk about nucleation and growth. But remember, there's bulk terms. Phase separation is beneficial because of that. But there's also a term that in addition to wanting to phase separate, we want to minimize the interfacial area. So there's going to be a certain interfacial energy of these domains. Okay, so first we go to spinodal decomposition and think about what happens. And the first thing is, why does spinodal decomposition happen at all? Because of composition fluctuations. So if I draw these composition fluctuations, here's as a distance of r, and I'm going to plot the volume fraction, let's just say of A as a function of r. And remember, initially, I prepared this at an average volume fraction of phi 0. So when we talked about it the other day, I drew that there was like one kind of fluctuation with one wavelength. So I drew something that kind of looked like this. But that's not true. I mean, certainly that fluctuation exists, but that's not the only one. There are also very long wavelength fluctuations. And there are also very short wavelength fluctuations. So something that kind of looks like this. And even shorter than that. So there's many different types of fluctuations. And they all have a certain wavelength to them. Let me draw the last one. Oh boy, this guy's really big. Something like that. So lambda 1, lambda 2, lambda 3. So there's all sorts of wavelengths. And the theory goes, and it can be proven, but the theory goes that, well, there's going to be an optimal wavelength that's going to win out. Why? Well, if I separate these fluctuations out, then one has to win for the following reason. So let's look. Oops, this is going to be R, phi A of R, phi 0. In fact, I'm going to copy this because I'm going to draw 3 of these. Duplicate. Tell you what, I wish I could do this on a chalkboard. Saves so much time. Of course, you're sitting there, hopefully with your pencil and paper, and you have to draw these. So feel free to pause the video right now. And now we'll continue. Okay, so if I have a short wavelength fluctuation, so one that I drew it in orange, so let me draw it like this. This is not favored. This is not a favorable fluctuation. Because at each of these points, this point is the transition from an A-rich region to a B-rich region, right? A-rich is high, B-rich is low. All right, so that's the transition. So this is an interface. And you can see if I have a very short wavelength fluctuation, so if lambda is small, I have many interfaces. That is not energetically favorable. So what's going to happen is these fluctuations are going to die out because they are not energetically favorable. Remember, in that free energy of mixing, we didn't say anything about interfaces. Now there's another layer on top. We've got interfaces to worry about. Now, I could have a very long wavelength fluctuation, like this. That's fine. You can see from the way that I've drawn it here, fewer interfaces. And the things are separated from each other. So you might say, well, hey, that's what I want, right? I have only one interface, or I have a minimum amount of interface, and the things are separated from each other. Sure, I agree with you. But the problem is that it takes time. It takes time for the particles to diffuse. So this is diffusion limited. In other words, it takes a lot of time. For the A particles to diffuse into the A-rich regions, and for the B particles to diffuse into the B-rich regions, it just takes a lot of time. So what's going to happen is this is going to be slow to form, and you're probably not going to form it because you're not going to have time. The reason you're not going to have time is because eventually, let's make this green because it's the good one, you're going to have some fluctuation form. Of course, all wavelengths of fluctuations are forming, but you're going to have one in particular that beats out everybody else. Why? Because you're going to have a minimal amount of interface. And you're going to have a size that, in terms of time, wins out. There's a certain size that will win out. So there will be a lambda max that is the dominant wavelength of the fluctuation. In other words, fluctuations with that wavelength win out. And it's from that initial state with that certain fluctuation that you're going to start growing your phase-separated regions. So the description of this is beyond the scope of this class. This is something that you might have at the graduate level. It's a fourth order differential equation, I believe, if I'm remembering correctly. I had to solve it. It's solvable. It's not that bad. It's just outside of our scope. And so this is described by the Cahn-Hilliard equation. One of the two people, John Cahn, he passed away in 2016. He was at NIST, which is where I worked as a postdoc. And then he was also on the West Coast. Hilliard, I forget Hilliard. But anyway, the Cahn-Hilliard equation you can use to rigorously go through this argument. We're not going to do that. But what you can do is from the Cahn-Hilliard equation, you can derive what you expect the dominant wavelength to be. What wavelength will win out. And what you'll find is that lambda max will be equal to 6 pi squared to the 1/2 power times the radius of gyration of your polymer times 1 minus chi s over chi to the minus 1/2. And remember, chi s is going to be the value of chi at that spinodal, on the spinodal line. Okay, so it's the value of chi that you have relative to the spinodal curve. Okay, so that's what happens at first. And so what's going to happen next, I'm going to talk about qualitatively. So you're going to have what we call the early time, the early stage of spinodal decomposition. So at the early stage, if you were to plot your composition as a function of distance across your system, then you would see something like this. And remember, I prepared my system initially at phi 0. And for whatever temperature I'm at, remember that the free energy of mixing looks like this. So this means that at equilibrium, my system will phase separate from whatever I had, phi 0, and form two phases, one with a composition phi double prime and one with a composition phi prime. And remember that the relative amounts of those, so if this is the beta phase and this is the alpha phase, remember that I can calculate F alpha as phi double prime minus phi 0 divided by phi double prime minus phi prime. And I can calculate F beta as 1 minus that. So that's how much of the two phases I'm going to form. And each of those phases will have the composition phi double prime or phi prime. So in terms of my graph, that means that up here, these are the limits. So eventually, when all is said and done, I'm going to have an A-rich phase. So I'll have a composition of phi double prime. And I'll have a B-rich phase. Phi prime. And I'm going to draw 3 of these. So actually, let me copy this also and duplicate it. Let's put that down here. So we'll paste that one. And we'll paste one more time. So that's what I'm going to have. While we're talking about it, the other thing to remember, this is also true, is that for the spinodal decomposition, remember that I've got those binodal and spinodal curves. So here's the binodal. Here's the spinodal. Initially, I prepared my system somewhere here. So this was phi 0. And then my system is going to phase separate spontaneously. And it will have a composition phi double prime. And phi prime. So remember all of these different things in terms of both the plot of the Flory-Huggins parameter and the plot of the free energy. All these things are true. So going back, this is what's happened. This is the mechanism or the underlying thermodynamics. So what does this look like in terms of my system? Well, I've got some optimal wavelength that's formed. And I can define a domain size. So R of t is going to be my domain size. It's basically the size of one of those phase-separated regions. And I can also define something like this. I can define a width to my interface. If that's really broad, then I have a really diffuse interface. If that was sharp, I would go from A directly to B. So I have an interfacial width. Okay. So in the early stage of spinodal decomposition, what I have is that R of t is similar to the interfacial width, and both will increase with time. So my interface will get wider, more diffuse, and my domain size will get larger also. With me? So that's the early stage. And then I move on to the intermediate stage. Let me move this down a little bit. And I will also move this down a little bit. All right, so after the early stage, I will eventually transition to the intermediate stage. And at this stage, I reach my stable compositions. So I reach these points on the plot of chi, or I reach equivalently these points. So my domains will have either a composition phi prime or phi double prime. So in terms of my graph then, what I'll have is something that kind of looks like this. And in this case, I'll draw it here. I've got my domain size, and it is not equal to the interfacial width now. And you can also see that I've reached my stable compositions of phi prime and phi double prime. And you can also see that I've just got in the middle, let me get the color right. Yeah. I've got whatever interfacial width here. And in this intermediate stage, what I find, let me get the colors right once more, is that R of t will increase with time. You saw that in the movie that I showed you, right? The size of that red region was getting bigger and bigger and bigger as time went on. So R of t will get bigger, and now the two phases don't like each other, right? So I don't want a diffuse interface. I want to get things as far apart from each other as possible that make sense in terms of the thermodynamics. So you'll find that the interfacial width now will decrease with time. And that's what I get at the intermediate stage. Finally, in the late stages of spinodal decomposition, well, I've got some domain size like that. And so this is still R of t. And this is still the interfacial width, so this is still W of t. But what you find now is that the interfacial width has reached its equilibrium value. That interfacial width is going to depend on the chi parameter. The larger that chi is, the sharper that interface is. The lower that chi is, the more diffuse it is. So what you're going to find is that W of t approaches what it is going to be at t equals infinity. So this stays constant. And then what you still see, though, is that R of t increases with time, because the larger that R of t is, the less interfacial area that you have. So the interfacial area is minimized. And so what you'll eventually get at the end of the day is, if I was to draw my system from the top down, eventually you're going to have one interface if you let this go forever, kind of like with oil and water. And so you're going to have one phase that has phi prime, and you're going to have another phase that has phi double prime as the composition. And so remember, from looking at either the diagram with chi or the diagram of the free energy, that phi prime will be a B-rich phase, and phi double prime will be an A-rich phase. So that's what I expect at equilibrium. The morphology of these things tends to look kind of wavy, kind of bicontinuous. So in terms of the morphology, it looks almost like the video that I showed you. You get these regions of phi prime that kind of go throughout your system in this wavy kind of pattern. Of course, eventually you want that single interface, but whether you get there or not in a realistic amount of time just depends. Certainly in computer simulations you can get there. But that's kind of what the system looks like after spinodal decomposition, or during spinodal decomposition. And so what you find in general, again, there's some real quantitative details that I'm leaving out here, is that R of t either grows as t to the 1/3 power, and this is a mechanism that was proposed by Lifshitz and Slyazov. And this is due to evaporation and condensation. It's a diffusion, it's a diffusive process. So what this means is that in order for your domains to grow, what you'll have is a particle from this phase evaporate from that phase and go into the other phase, and diffuse around randomly and condense into the other phase. So that's the diffusion, or the diffusive mechanism. If you get to the point where you've got bulk movement and hydrodynamic effects, then it'll grow linearly with time due to Sigia in the late 70s, I believe. And this is due to hydrodynamics. Or bulk flow. And so in that case, you get flow of these regions in your system, and that's why it grows the way that it does. And so those are the two main mechanisms. So if you plot the domain size as a function of t and measure that, then if you can get that exponent, just like we kind of do with the polymer chain size, that exponent will tell you something about the underlying mechanism of how this phase separation is proceeding. So that leaves one last mechanism, and that's nucleation and growth. Remember that nucleation and growth that's what happens in the metastable regions. So it happens between the binodal and spinodal lines. So between binodal and spinodal. So in terms of the phase diagram, if we just look at the phase diagram with chi, then here we go. Phi, chi. Here's my binodal line. Here's my spinodal line. Spinodal decomposition is going to happen when I prepare my system in a region like that. And then it will still phase separate to the stable points. So you're going to have phase separation to here and phase separation to there. So you've got over here a B-rich phase, or A poor, phi prime. You've got phi double prime. And of course, you prepared your system initially at phi 0. Now notice these compositions are not in the middle. They tend to be off to the side when you get nucleation and growth. So the way your system looks is something like this is initially mixed at phi 0. You get nucleation and growth. And then you're going to have these kind of droplet morphologies. So it's going to look like this. And so you're going to have a minority phase like this, phi double prime. And then these droplets of phi double prime will be embedded in a matrix with phi prime. Okay, you see initially that the way that I drew phi 0, it's shifted to low values of phi a. That means there's not very much phi in there. It's phi a in there. There's not very much a particles. So that means that this minority phase that forms will be a rich. And the matrix, or the majority phase, is B-rich, and you could calculate, just as we did before, how much of each you have. So you could calculate F alpha and F beta. And remember, things are a little bit backwards. F alpha will be the amount of the alpha phase, and F beta will be the amount of that phase. Pause, look at that, make sure it makes sense. Okay, and then we'll continue. All right, so we're going to have to think about what's going to happen here. We've got an interfacial term due to the AB interfaces, and we have a bulk term from the phase separation. So remember, delta F V is the bulk term. It's the change in the free energy. It's what we've been talking about the whole time. Everything but the interfacial term. So again, this is going to be delta F mix of, in this case, whatever volume fraction we have of that phase, minus delta F mix of where we started, which is phi 0. And this is going to be less than 0. So in addition to that term, we have an interfacial energy between the two phases. So we have that gamma term. So the total change in free energy upon demixing so the change upon demixing will be the volume of one of these droplets. I should say before we do that, these droplets will have a size r. So it will be the volume of one of those droplets, 4/3 pi r cubed, times how much the free energy is changing per volume, or the bulk term, when the system demixes. So multiplied by delta FV. And that term should be less than 0. And then added to that, each of those droplets is going to have a surface area equal to 4 pi r squared. And those interfaces between the droplet and the bulk phase, or the matrix phase, is going to cost a certain amount of energy. So it'll have an interfacial energy gamma, which is like joules per meter squared or joules per nanometer squared or something. So that surface area should be multiplied by the surface energy. So this will be the free energy change to nucleate one droplet when it starts to demix. Oh, I should say with size r. And you can see that there's competing effects. This term is less than 0. That term is greater than 0. So this term favors small droplets. This term favors a big droplet. It was like Goldilocks. There's going to be some happy medium that the system prefers energetically. Now you could plot what the free energy looks like. So this is delta F from that equation as a function of droplet size. And we can break it up into a couple terms. So you can see that the surface term scales as r squared. And this is greater than 0. So this term is going to look like a parabola. And it scales as r squared. And we also have another term. We've got the bulk term, and it's less than 0. And it scales as r cubed. And this is the bulk term. And the free energy is the sum of those two. So if you add those up, you're going to get a free energy that looks like that. So what you can see is there's an energy barrier right there. And the height of that energy barrier will be delta F star. And so you see that the free energy increases until you get to that certain size. And then once you get past that size, so delta F increases. Once you get past that size r star, delta F decreases. So one question to ask is, what is that r star? What is that critical size for my nucleus beyond which it will grow and lower the free energy? So in other words, if you were to nucleate, let's change colors one more time. If you were to nucleate here, the free energy goes up and droplet will dissolve. So you can form a little tiny droplet, but it increases the free energy, and so it just kind of dissolves back to where it was. If you can create a droplet over here, then the free energy goes down and the droplet will grow. So we want to find the size of the droplet beyond which making it bigger and bigger and bigger will decrease the free energy until eventually the free energy change goes negative. Well, you can see that that point is going to be an extreme value of delta F, and it's the maximum of delta F. So this means that the derivative of delta F with respect to R evaluated at r equals r star should be 0. So let's do that. The derivative is super easy. And so for the first term, we're going to get 4 pi r star squared delta FV, so that's taking the derivative of the bulk term, and then plus 8 pi r star gamma should equal 0. We can divide through by 4 pi, and here's one of those times where you have to be careful. We can divide through by r. So we know that because r is squared here, that there are two solutions to this equation. Fundamental theorem of algebra. One of those solutions is 0. I don't care about that solution. Let's get rid of it. That makes no sense. That's going to be the point where the droplet just dissolves and goes away. We want the size where the droplet's not equal to 0. The droplet radius is not equal to 0. So we can do that. We're going to get r star delta FV plus 2 gamma equals 0. So you can see that r star is going to be, did I miss a minus sign? No, I didn't. Will be 2 gamma over delta FV. Right? Remember, delta FV is less than 0, so the sign of these two things ends up being the same, meaning that r star is greater than 0. So as you're doing these things, keep all these little tiny details in mind, right? Because you want to make sure that your solution makes sense, that it's a viable solution. So here it is. You can see that your droplet size, the bigger the interfacial area is, the bigger the interfacial energy is, gamma, the bigger your critical nucleus has to be before you can start to phase separate. So if gamma is huge between the two phases, you might find that your system is metastable still, but that it's going to be metastable for a much longer time than if the interfacial energy is less or smaller. The smaller the interfacial energy is, then then the smaller the critical size is of the droplet that you need to nucleate. So first you have to nucleate your droplet, then you have to grow your droplet. Same thing for delta F. If delta F is big, if there's a huge energy benefit to phase separating the two components, then delta F will be big, delta FV will be big, and the critical nucleus size that you need to create is going to be pretty small. So if delta FV is really, really, really big, your system is not going to be metastable for very long. It's going to quickly phase separate. On the other hand, if delta FV is small, if the two don't hate each other too much, the two components, then you may find that you have a very long-lived metastable state. So you can substitute in and find out what delta F star is. I won't bore you with the details, but it's 16 pi gamma squared over delta FV. Okay, so those are the values that you've got. You've got delta FV that we solved for, delta F that we solved for, and R star. And so that's the nucleation and growth mechanism. First, we have to nucleate a droplet of size R greater than or equal to R star. And then the droplet grows. So those are the details, at least the kind of semi-qualitative details of nucleation growth and spinodal decomposition. So remember, it's going to depend where you are in that phase diagram in terms of what you're going to get, in terms of which mechanism is going to take over. But at the end of the day, what you expect is a system where you've got two phases. I'm just drawing them as circles here. Actually, let's not even do that. Let's just draw it like this. The shape of the domain is going to depend on the volume fraction. But no matter whether you have spinodal decomposition or nucleation and growth, you're going to create one phase that has a composition equal to the stable one of the stable points, which is phi prime. And then you'll create another region that has composition phi double prime. So you'll create an A-rich region and a B-rich region. So the last thing I'm going to do is put up some videos and talk through some of the results, just so you can kind of see this in action based on the output of my code. So last night I took the code that I've been using that I wrote such a long time ago, and I decided that I would run a new simulation. And it's amazing to me because in 2004, when I wrote this code, these simulations would take several weeks. In fact, I'm going to show you one in a couple of minutes that took over a year. The computer ran 24/7 for 365 days. And thankfully, the power didn't go out and nothing happened to it, because the way the code was written at that point, there was no save game. There was no way to restart it. So if it crashed, that was it. So anyway, it's amazing. Once again, these movies are made from an open source code that I wrote. And you can see the URL behind me here. You're welcome to go and look at the code and download it. And if you are interested in computer simulations, you're welcome to run the code. It's written in Fortran. The newer codes that my group uses, they're written in C++, but you can look at the source code and see how this works. But here's a 3D simulation. And look at this. I mean, you can see I don't want to say violence, but this is just a binary fluid, because polymers will behave the same way. It's just the dynamics will be slower. But you can see the fluid like sloshing when these things like phase separate. And what you're seeing is essentially oil and vinegar, like that kind of phase separation. So you can see it twists and turns and the fluids pull apart, and like the interfaces start rocking back and forth. Like it's really amazing for me to see this. So this took, I don't know, 4 hours to make, whereas before it would take weeks or months or sometimes years. And you can see a couple features. You can see that the particles, when the things completely separate, you can see that there are particles in the other phase. Partly because that's favorable, partly because they're leaving one of the phases and they're off diffusing in the other phase, and then they rejoin the other one. So you can see a lot of the features that we were talking about in terms of the process of spinodal decomposition. So here's another simulation that I made, and this is still spinodal decomposition, but this is in a thin film. And one thing that you can see is that, first of all, the visuals, the movies that we can make 15 years later, are much better than the ones that I made way back in 2004. So I'm showing you this thin film undergoing spinodal decomposition, because if you look in the big circular region, you can see again that particles are in there, and you can see that the particles are evaporating from the red phase going into the other phase that I'm not showing, and they're hanging out, and then some of them will rejoin the red phase, and then others will leave the red phase and go back in. So it's just so cool to see this. I'm shocked seeing these movies, because I've never been able to see them in such detail before. Okay, so those are two examples. One is like pseudo 2D phase separation, and then one was the full 3D separation. And so we're going to talk in the next couple of videos about how we might prevent phase separation from occurring, because blending multiple polymers together is a huge technological ability for us in order to create materials that have properties that we can modulate and tune to some extent. So what I'm showing behind me here is a simulation where now you can see both components. You can see the red component, and you can see the other component that I was hiding before that's in blue. And the idea of this simulation, which was published, the work took a lot of time. This simulation is the one that took over a year to run, 24/7. I started it as either a junior or a senior. I think I started it as a senior, like a rising senior. And it wasn't finished until I was in grad school, when we could write up the results. No, I might have started it as a junior, so it didn't finish until I was a senior. But anyway, the idea here was to put nanorods into the one component. So there's nanorods in the red component. The idea being that they're so jammed up in there that they will stabilize the structure. And it worked really well. If you did this with spheres, it turns out that it just slows it down. It doesn't stop the phase separation. With nanorods, we didn't prove it, but we provided a lot of evidence that nanorods, on the other hand, would stop the phase separation. And actually, we published this work, and several years later, I was almost out of grad school with my PhD. So I started this as an undergrad. I was almost out of grad school with my PhD, ready to go to NIST. And finally, there was experimental confirmation that what we predicted was true. This was super exciting for me. So a lot of work went into this simulation, a lot of perseverance and blood, sweat, and tears to get this result. So the other thing that we thought you could do is, instead of having the nanoparticles go into one of the components, either the red or the blue, what if the nanoparticles went to the interface and could somehow jam the structure? This was predicted by some other groups, and we decided to carry out a DPD simulation to look at whether this would be true. And when we looked at really small particles, it was kind of disheartening. You can see the red component is undergoing the normal spinodal decomposition that I showed at the very beginning, and the nanoparticles that are supposed to go to the interface between the red and the blue just aren't going there. And so this was kind of a surprising result. The reason they're not going there is because they're so small that entropy is winning out. They would much rather be dispersed throughout both phases than to be confined at the interface where their entropy is reduced. So then we thought, okay, well, what if instead we look at bigger particles? Is that going to work? And so the next video I'm going to show you is the result of using bigger particles that adsorb to the interface and how those jam up the structure and prevent full phase separation. And so here you can see the result of using bigger particles. They actually prevent full phase separation. So you can see that there's this ribbon-like bicontinuous red structure that's going throughout the system, and it doesn't completely phase separate into the two components. And when you make the particles larger, they start to go to the interface and jam up the structure. This kind of structure is called a bigel, B-I-J-E-L, as in a bicontinuous gel. Realizing, of course, that gel is G-E-L, but that's what they're called. So this is a really important class of materials that a lot of people study. And so here's just a DPD simulation of a bigel, and you can see the effect of the nanoparticles going to the interface on stabilizing the structure. And so this is the experimental result, the simulation result. And other people did this, but in particular, my PhD advisor, his group was looking at the experimental confirmation of this. So these simulations were found to be in great agreement with the experiments that were done on thin films. So the point I'm trying to make, in addition to just showing you these really cool simulations of this process that I hope can help you visualize phase separation, the other point I'm trying to make is that computer simulations, even with a really simple model like DPD, can be incredibly powerful techniques that you can use to kind of predict what your material will do and predict maybe new ways of blending multiple materials together. And so again, in the next video, we're going to look at some of the ways that we might or the strategies we might take to try to blend in the different polymer components to basically get materials that have the physical properties that we're interested in.